And so this talk is about Bognor means on Heisenberg groups, and maybe I should like introduce like the main objects that we are going to like work with in this talk. So one is like the Heisenberg group. So just as a space, Heisenberg group is like R to the 2n times R with the following group laws, or like X is actually an element of like R to the n, and U is like an element of R, which is like corresponds to the center of the group. And then the group law is given by, well, in the first component, we are going to add like X and X prime. And in the second component, or like in the like central component, we are going to add U and U prime. And here we have like this additional twist coming from the first layer. So here we have like the standard symplectic form. So this is like going to be the identity matrix on R to the n. And we have like this inner product with respect to J. So like this skew symmetric form here. So that this is like the Heisenberg group, and we are going to look at like the following like left invariant operator on the Heisenberg group, which is like the following like sum of squares operator, which is like defined in terms of these left invariant vector fields on the Heisenberg group. Like for the remainder of this talk, one doesn't have to like memorize like the explicit form of these vector fields. The important point is that we have like some basis somehow on the first layer, and then we have like this sum of squares operator here. And okay, why do people actually like look at this kind of operator? Like the main motivation why to look at this operator is that this like some in some sense like easy model case of a non-elliptic second order linear differential operator. And like its elliptic analog, so like some analog that one can like think of is like on Rn, this would be like the usual negative Laplacian, where these are like the usual partial derivatives. But like the special feature of this operator here is really that this like non-elliptic. And so let me collect a bunch of facts. So to introduce like the main question and also like the main problems that we are going to look at. So first of all, this operator is with respect to the inner product on L2. This operator is positive and also has a self-adjoint extension, and we are going to identify its self-adjoint extension with the operator itself. So in the following, we will just say that this operator is actually like self-adjoint. And well, since it is like a self-adjoint operator, we have like some functional calculus available, which in our case means, well, if we have like some spectral multiplier here, which lives on the real line. So, I mean, we are only seeing like the part like the positive part of the real line here, since our operator is positive. So we have a like positive spectrum. And so like so given such a spectral multiplier, the spectral theorem tells us, well, we can define like some operator M of L on L2, maybe some unbounded operator depending on like our spectral multiplier. And so first of all, this is going to be like some operator on L2. And the spectral theorem immediately tells us, well, this is going to be like some good operator, some bounded operator on L2, if and only if M is like bounded almost everywhere. So here, like, let me note that like here, we have like some perfect characterization of like L2 boundedness in terms of, let's say, properties of our multiplier. And the question that I'm interested in, well, what's going to happen if we are going to replace L2 by like say LP here? Can we also like characterize like LP boundedness, maybe in terms of like some regularity properties of our spectral multiplier M? So that's like roughly the big picture. So that's like our main question. We want to characterize like LP boundedness just in terms of like some properties, maybe some regularity properties of our multiplier M. And what's some model result? So let's to return back. So we've been talking about like the Heisenberg group and the sublaplacian. Let's return back to like our other like elliptic model case. So for the elliptic model case, it's like known since like the 60s due to Hermander and Michelin that whenever we have like some order of regularity, So this is going to denote some localized Sobolev norm. And again, one doesn't have to remember like the explicit definition of this one. It's just like some, well, localized Sobolev norm here. And S will denote the order of regularity here. And like a special case of the Miquelin-Hermander theorem tells us that whenever we have like at least regularity of half the topological dimension, then we actually get LP boundedness on all LP spaces simultaneously here. And also like for the endpoints, one has like some weak type 1, 1, like for the case where P is equal to 1, one at least has like some weak type 1, 1 boundedness. And okay, so like that's the situation for like the Laplacian on Rn. And there are also like similar theorems known for our operator, like the sublaplacian um, on the Heisenberg group. So this is exactly the same slide as before with, well, just like this part here changed. So there are like certain analogs where D is like the topological dimension. And let me mention that, I mean, for us, we had like this group, well, which was R to the 2n times R. So in our case, like the topological dimension would be 2n plus 1. I mean, like in this business, there's also like other notion of dimension around with it, which is like the so-called homogeneous dimension. But we are interested in like proving like theorems under the like using the topological dimension, like this one. So the following analogs are known since the 90s due to like Hebisch and also due to my former advisor Detlef Müller from Kiel in Germany and Elias Stein. For sublaplacians on like Heisenberg groups and also like some generalizations on Heisenberg, like some bigger class of groups, the so-called Heisenberg type groups, it is actually known that the similar theorem here holds true with, well, essentially like the Laplacian here replaced by L under the same sort of regularity condition. And then like 10 years or so, there have been also like some generalizations of like this result here for like more general classes of like stratified Lie groups. But like for this talk, I just wanted to focus on like sublaplacians on Heisenberg groups. Okay, so like the situation that we have here is kind of where we have like some sort of regularity condition, in this case, like half the topological dimension. And if we are good, then we are able to show like LP boundedness on all LP spaces simultaneously. But the question that I wanted to look at is like some refined version of like this question. Namely, let's say that we are going to fix a certain P here, and then we are wondering if, well, we have a similar result, namely if we have like a certain order of regularity, which might depend on P, well, then we wonder if it's also like possible to have like LP boundedness for this fixed P. So like this is like the P-sensitive spectral multiplier theorem. So we are wondering, well, if we can find some minimal threshold, which might depend on P, such that if we have like such an order of regularity here, that we have like LP boundedness for like this certain P here, where P is between 1 and infinity. Okay, returning back to the analog or like the elliptic analog for the in the elliptic case or like in the elliptic model case, it is like actually known like since well the 70s or 80s. So Charles Pfefferman did the Wagner-Weiss case here, and like Mike Christ and Andreas Seeger did like the more general like more general piece sensitive case here. So like they were able to show that actually like the threshold were well the threshold d times 1 over p minus 1 half is like a sufficient condition such that we have like LP boundedness here. And maybe let me mention here that well if we like formally set p equal to 1 here, then this reads like well 1 minus 1 half, which is like d over 2 here, like formally for the case where p is equal to 1. So And in this case, one can like do like some interpolations between like L2, L2, and then by some, well, again, by some duality argument, like it is possible to somehow to recover the whole LP range. But like this threshold here gets smaller if P grows. Then this threshold here is like smaller. And like this threshold here is shown to be optimal, well, at least in like this range, which for P, which depends on like the dimension D, like if like the Laplacian is lives on R to the D. And this is actually like the same range that shows up in like in Fourier restriction theory, which is also like used as like main tool in like proving that this threshold here is sufficient. And yeah, let me also mention that like this special case of like this multiplier here corresponds to the Bochner-Ries case. And yeah, so that's like the picture for like the elliptic picture. And for like the case for like sublaplacians on Heisenberg groups, well, first of all, there are like some bad news since like these results kind of rely on like exploiting like some, well, nice like some sort of Fourier restriction here. But like unfortunately, like in the group setting, in the Heisenberg group setting, like the Fourier restriction approach com fails completely or breaks down completely, which is like the following result. So my well, my former advisor was like able to show like 30 years ago or so that actually like the so-called Strickers projectors, which are formally given by plugging in L into like the following Dirac delta here at like lambda, where lambda is some like real number. These are actually like unbounded from LP to LP prime. And like the bottom line is that Fourier restriction or like any analog of Fourier restriction somehow fails completely in the Heisenberg like group setting. But like the one other thing is that if the center of the group, so remember our, as I said, the Heisenberg group is R to the to n times R, and if like so as I told you, like this here is like the center of the group. So here the center of the group is one dimensional, but like if we pass to some bigger class of groups where the center also might be like higher dimensional, then it is actually possible to like exploit some Fourier restriction phenomenon to establish like a P-specific spectral multiplier theorem. And this is actually what I did like 2 years ago in my PhD thesis, namely showing that if one is like that one is able to show like in at least in some range which depends on D2, where D2 is like the dimension of the center of the group, a similar result where we have like order of regularity D times 1 over P minus 1/2. And also, yeah, let me mention here, if we formally, or if we plug in D2 equal 1 here, well, this is going to read 2 plus 1 over 1. Yeah, just a second. 1 plus 3. So this is like 1. So this condition here would be an empty condition. So like this theorem would doesn't tell us anything about the Heisenberg case. So the Heisenberg case here is like kind of missing, and we have like some bad news since like, well, the Fourier restriction approach somehow breaks down completely. So in the result that I wanted to show you, we were actually able, well, despite the fact that the Fourier restriction approach fails, we were still able to show, uh, well, some result of that kind in like some non-trivial range for of P's on like the Heisenberg group. So here, like the P range depends on like the topological dimension of the group, and as well, the P range gets better if the dimension of the group gets bigger. So we have a similar result, well, namely, well, if we have like order of regularity, which is like D times 1 over P minus 1/2, then we have like LP boundedness on like this certain or like for this fixed LP space here. And as a corollary, one also gets like some result for Bognor-Ries means and uh, like Ries multipliers. So like this, the main result of today's talk that I wanted to show you, and in the remaining time, I wanted to briefly to discuss like the methods or like the tools that we've been using in this proof. So, okay, so I wanted to focus on the proof of like theorem A. And what we did is we showed actually some the following estimates. So here, so this is like defined in terms of the functional calculus of our operator L. So remember that L is a self-adjoint operator. So this is like the half-wave propagator. And we actually showed like some LP to LP bound for like this square function estimate. So we have like, we are going to look at the wave equation, and here we have like the half wave propagator. And first we are going to average in L2 over time, and then we are going to show an LP estimate here. And we are going to establish this under like this order of regularity here. So like this additional decomposition here can be thought of as being like some dyadic decomposition. So lambda should be thought of as being like some dyadic parameters, maybe like 2 to the j. And then we have like this. If a lambda grows, we see like some sort of blow up here. But like the blow up is controlled by this order of regularity. And in later, well, if one tries to establish like theorem A using like theorem B, um, well, what like the order of regularity that will pop up is like d times over d times 1 over p minus 1 half. So like this part here. So like this is somehow like the picture we are going to like show like this square function estimate B here, which helps us to prove like the spectral multiplier theorem A, since like this road here is like kind of closed since yeah, full restriction fails for the Heisenberg group. And yeah, let me tell you a bit like how we actually proved like theorem B here. Oh, and yeah, the motivation, why such a theorem is helpful. It's like again motivated by the elliptic analog of the sublaplacian, which is like the Laplacian. There, it is actually known that like Bognor-Ries is equivalent to a certain square function estimate for this operator. So this is like the motivation why we actually started like looking at these square function estimates here. And in the remaining time, well, I wanted to give a brief idea how to analyze this sort of operator, since like our approach relies on FIO methods. And well, I wanted to show you how like the FIO approach comes into like the picture. And so first, so this is like the estimate that we want to show here. And first, I want to explain you how to actually reduce this to an sort of like oscillatory integral operator. So we have like some integral operator where the kernel itself is an oscillatory integral. And first, we are going to derive some explicit formula for the Schrödinger semigroup here. So note that, well, we have an L here. So this is like not a typo, this is an L, this is square root of L. But well, in just a second, we are going to use like some sort of subordination formula somehow to relate this one and this one. So first, we are going to focus on this one. And so first of all, this operator can be rewritten as like a convolution operator, similar as for the Laplacian, but here with respect to the group convolution. And if one like puts this down explicitly, well, we actually have like Euclidean convolution up to this skew symmetric term here. So remember like this matrix here, this J matrix was actually like the matrix from the very beginning on like our very first slide, where we had like the identity matrix here and like this symplectic form here. Okay, so we have like some sort of like we have like some convolution here, and this is like our convolution kernel. And like one common thing that one does in this business is doing a partial Fourier transform with respect to the second layer. So remember we have variables x and u, and we are going to do a Fourier transform with respect to the just with respect to the u variable. Then like our like operator gets well turns into like a whole family of operators which are indexed by L to the mu. So this is like one operator from our family. So this is like one thing. The next thing is that like this partial Fourier transform here is compatible with the group convolution in the following sense. If we are going to define the following like twisted convolution, well, it's almost this like usual convolution except for like this like skew symmetric term here. So this here's again the skew symmetric form. So the bottom line is just well the like the convolution is compatible with like this partial Fourier transform. Um, well, in the following sense here. So I'm just telling you all these things to like understand the following like three lines here. So it's better to read this starting here. So we have like the Schrödinger semigroup applied to some function f, and then we are going to do the partial Fourier transform here. Okay, so first of all, this turns into like this whole family of operators here. So like functional calculus is also like compatible with the partial Fourier transform. So we have a like whole family of Schrödinger semigroups here. Okay, so on the other hand, we know that this is like some sort of like convolution here. And then we know that, well, that this partial Fourier transform is compatible with like this group convolution here, like yeah, like using this twisted convolution here. And my point here is, well, it's actually possible to write down like an explicit description of these, well, families or like of this function here, which is like the following. And like this formula comes from like representation theory of like the Heisenberg groups, but I don't want to dive into like details here. The point is just that we have like some explicit formula. And the point in this explicit formula is, well, we have like certain singularities here, which come like from the sign here. And so if we, okay, like remember T is, so like in our square function estimate, we had like T is between 1 and 2. So this is like just some bounded parameter. But like the mu part here, this causes really some trouble here, since here we are going to, well, uh, mu could be like any number, like real number here. So we could certainly like run into like singularities with a sign here, the, which is why we are going to need to do the following decompositions. So the first one is we have like for, well, for each zero of the sign, we have like a singularity here. So first we are going to decompose like our operator with respect to all these singularities here. And then we choose a diet decomposition. So we have like smaller and smaller pieces if we get closer to these singularities, which is essentially the following. Okay, this can be expressed in like, well, maybe some, well, one possible way to do this is to use the joint functional calculus of like L and like this, uh, like partial derivative with respect to the central layer. But the bottom line is, well, first we are going to decompose like the operator with respect to this all these singularities from the sine function, and then for each k we are going to choose like a dyadic decomposition of like pieces that gets like smaller and smaller to the singularities. So we have like two indices, one is k and the other one is L. That's the main takeaway. And then we have like the following subordination formula. So remember I mean, actually we want to analyze this operator, the half-wave propagator, but like we have like some formula for the Schrödinger semigroup, but it's actually possible to do use like the Fourier inversion formula, and then like this integral here is just like somehow the main part coming from like the Fourier inversion formula by a stationary phase analysis. So in total, so we are going to replace this operator by like this subordinate, like this whole subordination of like Schrödinger semigroups here. And then we have like the following decomposition. So we have first some K decomposition and then like some L decomposition. So L is like this dyadic decomposition into like smaller and smaller pieces. And well, if one somehow puts everything together, so like the convolution kernel that one ends up with is like the following. So like the sigma part here comes like from this like subordination trick, and like this tau part actually comes from like, remember we did this partial Fourier transform. So there's some other integral involved, and the second integral comes like from like reversing the partial Fourier transform here. And the point is that we are going to end up with the following phase function here. And like this phase function here has actually some geometric meaning. Namely, if we compute like the critical points of the phase function, well, there are like we have get some concrete formulas for those. And if one is going to plot like the, well, set of all these critical points, this corresponds to, yeah, the singular support of the half-wave propagator. So and it actually looks like this. And yeah, perhaps this should be like my last slide here. So in the Euclidean setting, the corresponding picture would just be a sphere, um, depending like on the parameter t here. But like in the Heisenberg case, like the picture is a bit like more complicated, and geometrically one can like think of like this decompositions here to correspond to the following pieces of the curve. So the k equals 0 part is like this yellow part here of the curve, and the KL part, where we get like closer and closer to these cusps of the curve, these correspond to the like the singularities of the sine function. Sine function. Here we are just seeing like a certain part of the curve. And like one feature here is that, well, for this part of our operator, we are essentially just supported like spatially, like in this blue box here. And yeah, so it's at least how the FIO approach comes into play. And maybe this is also like a good point, like to stop here. Yeah, so thank you.
Thank you. Yeah, right. Uh, that was very nice. Lars, could I ask? Well, actually, two comments. One is that a long time ago, Andra Hulaniski proved an explicit formula for the heat semigroup and this
Mhm.
for the Heisenberg group. And
Mhm.
if you haven't looked at it, I recommend it. But it might be relevant for some of the questions you do. And that's number one. Number two is, again, a long time ago, I formulated in myself a general theory of subluxations on any Lie group, and
Mhm.
some of the properties you discuss here for special cases might carry over to more general cases. So those are two.
Yes, I
two
mean this would like probably be the like next step, but like in for so I mean like but like in the groups that I'm working on is like usually like restricted to the two-step case, and like even for
Right.
these Hermander theorems that I've mentioned at the very beginning, it's like I mean for the best of my knowledge, it's like not even clear if like the corresponding like theorems even hold like in the three-step case. So yeah,
Oh, I see. Okay. Right. Yeah.
yes, but
Okay.
like yeah,
It's
but yeah.
fascinating that the difficult questions, even in small Heisenberg.
Yes, it's like even like the smallest, like or like
Right.
like easiest, like sub-elliptic case actually turns to be out to be
Okay.
like pretty complicated.
So
Yeah.
so the the main tool going into deriving an explicit formula for the is no, uh, using two independent Brownian motions to realize representations of the Heisenberg group.
Mm. Yeah, yeah, kind of. Yeah, and also like I mean these Miller type formulas, and I mean
Mhm.
these come like as you probably know, I mean from like representation theory exploring like certain like identities for like the Hermit polynomials and
Oh, right. Oh, yeah, absolutely.
yes, yes. And it's also like, I mean, actually, I mean, if one somehow tries to generalize this, I mean, okay, like there are also like similar formulas that are also like manageable for
Mhm.
Heisenberg type groups, but like passing to like some other, like some more general class, for example, like Metivier groups or like even two-step, there this formula like gets like, well, like a bit more like messier and like
Okay.
harder to handle.
Okay.
Yeah.
Okay. Fascinating. I'm really, yeah, I really enjoyed your talk. Yeah. Thanks.
Thank you.
If no more questions, let's thank the speaker, Lars, again.